Hi, I'm Adam, and this is my 16-bit computer from scratch. In the last video, I was able to salvage the fetch and instruction registers from the old build and integrate them into this iteration. I was able to manually input an instruction and watch the control signals get selected. I boldly declared that I was executing NOP instructions even though I don't have a program counter integrated. It was a stretch to be sure. Off camera, I worked on a few things that needed to be cleaned up. I addressed the power distribution concerns I had by dropping power and ground connections to multiple places on the build. I know it's not pretty, but it gets the job done. I also cleaned up some of the signal wires by changing them to longer ribbon cables. This eliminated the intermediate breadboard I was using to jump signals from one side of the build to the other. Finally, I worked on upgrading the temporary power and ground wires between the clock and reset modules, replacing them with something a little bit more robust. In today's video, I'm going to start by ignoring the program counter concern with the NOP instruction. Instead, I'm going to work on getting a break instruction fully operational. This instruction will place the clock into single-step mode when executed. I believe I have nearly everything I need in hardware to do this, and I believe I'm just missing a single signal wire. We'll see how that goes. Software and firmware, on the other hand, are a different story. The break instruction is not yet implemented in the assembler, it's not yet implemented in the control logic, and it's not yet implemented in the emulator. I want to get all that working prior to working on the hardware. Once that is complete, I will bring my program counter with its bodge breadboard into the build. I have some cleanup to do on the breadboard, making the hookup wires look better. I'll do that off camera. This is already tested from video 88, and I should be able to integrate the program counter easy enough, but we all know that easy enough doesn't work out that way for me. The last item on the video will be to integrate the program ROM from the old build. This ROM will take the address from the program counter register and output its contents to the fetch register. This final addition will allow me to write a program which will properly execute NOP and break instructions. Even better, I will have all the hardware I need to implement a jump instruction. By the end of this video, I will be executing a real program from program ROM. Let's make this all happen. I need to decide where in the instruction set the break instruction is going to live. Now, I've got these grandiose plans here about how these instructions are going to be organized, and you'll be able to discern by looking at them exactly what the instruction is. I need to throw this away for the moment because I need to focus on something far simpler than the big picture. I can iterate my way up to the big picture. So what I'm going to do is I'm going to go ahead and clear out this and just add the break instruction as the next instruction in the sequence. Now, I've also done some cleanup here on the instruction tables, just so that I can use some macros to fill the table in and make it actually a little bit more readable than it was. In particular, I have an opcode that is 1 byte long and has no args, and this is what that entry looks like in the table, so I can use that to determine my NOP instruction. I also need one for my break instruction. And again, we decided that that was in position 001, with the leading nibble being the conditional execution. Not implemented yet, so I'm not going to muddy the waters with it. Now, that also updates this opcodes. So I now have a break instruction in the opcodes that I can now turn around and implement. So I wrote this really simple test program. I'll end up adding to that as we go through this video. It has just a simple break instruction here. And then to get that to assemble, I had to add that into the lexical analyzer so that it recognized the fact that there was a break instruction. The next step here is the control logic. Now, again, I've removed a lot of the noise here, and the next order of business here is going to be to create my break instruction. There's my break signal. Okay, the first thing I want to do is I want to remove this break button. It is there to put the clock in single step mode, but I have a button on the clock to put it in single step mode. So I'll remove the break button and tie the control signal back to the control logic so that the instruction itself can now assert that break signal out and put the clock in single step mode. I'll be right back with the test with that. Okay, the big problem I have at this point is remembering what I named this control. I'll start by searching the text, closing out all the KiCad documents. That leads me to the signal it gets attached to. That finally leads me to the connection I make with the variable name in it. All right, time to go delete this and clean up the resulting mess. And a quick test. Next, I'll make the connection from the control logic midplane into the clock. That way the break signal will actually change the clock into single step mode. Let's try that again. That looked like it might have worked. Okay, so this first test puts me in single step mode before I'm ever out of reset. This brings up one of the problems I needed to solve with the memory. So let me change my test. Okay, so I'm going to put a no-op instruction ahead of the break. The purpose of this is to make sure that while it is clocking, it's got zeros there. I will have to address that when I put the memory module in, but right now I do not have that built into the emulator. And so test this, I have 7 steps to go through here before reset is complete. I'm going to work on trying to whittle that down. I think I can get away with 2 steps, maybe 3. So we'll see how that works out. I'll play with that offline. And yes, this does actually break the CPU properly. I do have to single step once in order to get past the instruction, but then I can go back to the adjustable clock or the oscillator. So that's working well. If I didn't want to have to single step to get past it, I could add a 74HC123 IC into the mix and have it create a single pulse that just triggered the break. And I may do that when I get to the PCB. The final order of business here is going to be to actually hook up this break. Now, to do that, I need to pull this low signal here, which is my break input into the clock, and I want to replace this with a control signal coming off of the control logic midplane. I believe that's the location, but I'd have to double check the schematic. It is not. It is this one that is where it needs to be plugged in. Let's give that a shot. Now, as I power this up, it should go through its reset cycle and be executing no ops. If I change the input of this signal from low to high, that'll be the break instruction and should cause this clock to stop. Okay, so I'm no-opping without incrementing a program counter. To make that high, I now break. I'm in single step mode. I can single step my way through this. I can put it back to a no-op, single step in a no-op instruction into the fetch register, single step past the break instruction, and now I can run again. So that's awesome because now I can actually break the program on entry or wherever I need to and put the clock into single step mode programmatically. That'll allow me to get very deep into a program and even conditionally break the CPU when I'm looking for a specific condition I need to debug. This is awesome. The next order of business here is going to be to reintegrate my program counter along with its Breadboard and tie that in down here, and then actually be able to increment the program counter using the no-op instruction. While I'm hooking this all back up, I want to call out that I did quite a bit of cleanup on that breadboard. Okay, generally speaking, that is better. Now I just need to take this cable and hook it up into the program counter control logic. Drop that down here so I have the control signals coming in. Then I've got 2 additional signals I need to pull in. I need reset hold and I need the CPU clock. Reset hold should be able to come from there. And then the CPU clock should be able to come from here. And this, I hope, are all the connections that I need in order to step through this. Let's give it a shot. And I'm executing a no-op instruction, or fetching a no-op instruction, executing a no-op instruction. And as you can tell, the program counter is incrementing. I'm incrementing before I actually get out of reset. That is not the desired result. So am I picking up the correct hold? Okay, so my CPU clock is pulled from my CPU clock signal on the clock. My reset hold is pulled from reset hold up here on the reset circuit. I'm thinking this through because yes, this is how many clock cycles after the copy is complete that this actually executes, so that's good. My 10 block signals are coming off of my 10 signals here. I will have to update the interface point for the general purpose register. But powering this on, it resets and it immediately starts counting. Now I can reset again and it immediately starts counting again. So if I reset and force it into single step, 1, 2, and you can see it's cleared program counter, 3, 4, 5, 6, 7. It's going to come out of reset now. So that's now address 0. And then it jumped to address 2. Why did it jump to address 2? That then is a problem because I'm incrementing when I shouldn't be incrementing. Now the problem is my output here might be questionable. I may need to put this through some kind of a buffer to drive that better. Okay, let's try this. This is a 74HCT541. This is an 8-bit line driver IC that I want to try to squeeze in here. I need power and ground. Two signals to enable the output, and I want this always enable. And I am going to take the clock signal directly off of the output here and drive it into two of these inputs. Now I'm going to take this output from here, that output from there, and this should in theory split those signals. Haven't missed a beat yet. Now let me try that again without this capacitor in there. Okay, that's going to work perfectly. Now I am not going to put this on the actual clock. I'm actually going to put this on its backplane. But I can now reset, and I am actually executing NOP instructions because I'm actually incrementing a program counter. The last thing I want to do in this video is I want to integrate my program ROM. I'll start with power and ground here. Here I have the output of the program ROM, which becomes the fetch bus here. These two will become the inputs into the fetch register. I can get rid of this and replace these signals with what is coming off the program ROM. Next is the input into the program ROM, and this is going to come off of address bus 1. Now this is the output of the program counter. I need a reset hold signal, and I need that inverted so that the outputs of the program ROMs are not going to be asserting while I am in reset. So I will pick that up here, and I'm going to want to add that to this board here at some point. The last thing I want to do is I want to take the main bus, and I'm going to pick that up here, and I'm going to drop it over here on this side, just up off the screen up here. And this is going to be used for a jump instruction, which we will implement as part of this video as well. So that then should allow me to do jumps as well. Now, I have no idea what's on these two program ROMs, and they certainly are not going to be built for this particular set of control logic. So I am going to write a purpose-built program to test fully the no-ops, the break instruction, and a jump to an immediate value, which would be presented off the fetch register. Okay, let me get that written. Okay, this is the program I used for debugging the emulator. Let me modify this program so that it now also handles the jump instruction. Now, I no longer want to start with a no-op because I want to make sure that my control signal for reset is not presenting anything out onto the bus. And so I've got a break followed by a no-op instruction just to stop everything right in the beginning. And then I've got another break, a few no-op instructions, and then a jump back to that second break instruction. Now I don't expect this to assemble. And the reason I don't is because of my jump instruction here. Unknown instruction on line 30. I guess I've got a little bug there. So let's go ahead and dress up my assembler. So I do have my jump already built in here. Here I'm working on a helper macro for the assembly tables. I need this for an opcode that takes a single immediate parameter to the instruction. This is quite fussy. I'm not sure that this is going to persist, but I'll hang on to it for now. Okay, let's see what that does. And amazingly enough, that worked. I want to take a look at the binary that was produced out of actually the text. Let's take a look at the text out of this. 0002, 0002. It's unfortunate that that lined up like that, but that is actually accurate. All right, let's get the control logic fixed up here. Okay, now I'm going to need to update the emulator because the emulator itself does not take advantage of that inverter properly in order to handle the reset hold. I've got a reset signal, but I don't have the reset hold signal. So let me update that. Okay, I'm going to move through this rather quickly. I ended up going down an incorrect rabbit hole and ended up discovering my mistake and going back and correcting it. Let's jump right into the testing. Yeah, let's try that again. Okay, add a reset. And there's my break. Single step past that. Back to the adjustable clock. Breaks again. Single step past that. Go back to the adjustable clock. And I went back to 2. That is working properly. Next step is to reprogram all the EEPROMs. Okay, I now have quite the mess going on here. I'm going to have to do something to clean this up and get it all straightened out. But I am hooked up. I have my control ROMs reprogrammed. I have my program ROMs reprogrammed. And so now I should be able to execute that code that I was just executing in the emulator. Let's see what we got. Okay, somehow I am immediately into single step mode. I don't know exactly how that's happening at this point. This could be related to garbage coming from here on startup. So I will have to investigate that. I'm still at address 0. I am still in reset. So if I put it back into the adjustable clock mode, it now gets up to, well, it went to address instruction 2, which is a break, which is correct. If I single step past that, put it back into adjustable, I'm now back to a break, which operated correctly. Single step past that, back to adjustable, back at a break. Again, this is at address 4. Okay, I think I need to clarify something here. The instruction in the instruction register is address 2, which is truly the break instruction. The instruction that's in the fetch register was at address 3, and the next instruction that is going to be fetched is at address 4. I'm not quite sure how I feel about that yet. I may need to play around with that a little bit and potentially display that in some different manner. Right now, I'm going to go with it. So let me keep this in single step for a moment. Address 5, which is a no-op. Address 6, which is a no-op. Address 7, which is a no-op. I've got my jump instruction coming up here. So there's my jump. There's my target address. That's address 8. I've got all my control lines lit here. This is now jumped back to address 2, which is correct. So the immediate value of 2 was replaced with a no-op going up here into the instruction register. This has been replaced with a no-op, and I don't know if that's been replaced with a no-op coming from the next instruction after the immediate, or if that's a no-op naturally occurring. I need to write a test for that. But then here is my break instruction, which was instruction 2. Instruction 3 is being fetched, but there's my break. Let me make that quick change, and let's see if we can figure out if we've got a different problem. Okay, to make this change, I should be able to come in here and do a data byte 0xFFFF. Is it a data byte or data word? I believe it's data word. So that should turn on every single LED on the fetch register if that's actually what's coming in. Let's build that and reprogram it. Okay, program ROMs have been updated and reprogrammed, and now we'll check to see if we actually get all the bits loaded here as we execute a jump instruction. I think the probabilities are pretty high here. So I'm going to single step my way through this, go through reset. Out of reset, address 0 is a no-op. Address 1 is a break instruction. Continuing on, there's my jump with the target address. And yes, as a matter of fact, it is. So to do this, I need to change the assembly instruction to include a no-op immediately after the address that we're jumping to. This will force a no-op into the fetch, which then should allow it to flow right up into the instruction register. So what do I need to do here? This needs to turn into a 3-word instruction where the first word is 0002. This really should be 0 because that's where the immediate value should be placed. And then this should then be a 000, which follows that up. Now, if I rebuild this, and now I take a look at, let's go take a look at, here is my jump instruction, least significant byte. Here is my jump target, least significant byte. Here is the trailing no-op, and then here's my data word, which should be my litmus test as to whether or not this is working properly. Let me reload this onto the program ROMs. We'll give this a test. Okay, the program ROM is reprogrammed again. Let's give this a shot now. Single step through reset. There's my jump instruction. There's my jump target. This is now loading a no-op afterwards. I did properly jump to address 2. And that now works. So it runs until I hit a break instruction. Another break instruction. So I have to single step past that. There we go. That's working perfectly. Now, there is a problem. I am paused on a break instruction, and if I reset, I still go back into single step mode. I have to single step my way through reset. If I reset when I'm not in at a break instruction, it does properly reset. Okay, so this didn't quite work the way I had anticipated. Apparently there was a break instruction that was still in the pipeline waiting to get up to the fetch register that ended up clocking and then putting the clock into single step mode. But if I reset while I am at a break instruction, it holds it. The solution is going to be related to the 74 HC123. LS in this case, but I need to get an HC123 and turn that into a rising edge detector for the break signal so that it no longer holds that, and I end up with a high going pulse that is asynchronous to the rest of the clock. Now, I'm not going to do that in this video, but I am going to put that, I've got to get some HC123s on order. I will get that ordered and we will include that into the build here shortly. In the meantime, I just need to single step past the break instruction to reset, or reset and single step my way back out of reset. Okay, there's one last thing I want to take a look at here, and that is trying to optimize just a little bit that jump to an immediate instruction. That's going to happen a lot in the course of running a program. So if I can save a word per instruction when I'm jumping to an immediate, it's going to end up adding up quite a bit over time. So what is it that I think that I can do? When the jump instruction is up here, let's put that up there. When my jump instruction is up here, it's already suppressing the output off of this fetch register latch into the instruction register. So this is already presenting a NOP out onto the control logic so that it can latch a NOP. The problem is that the control ROM is still actually outputting the next instruction, which is why I had to make that a NOP explicitly. Well, I have a fetch suppress signal already built into the control logic here. And if I use that fetch suppress signal and tie that into the control ROM, I should be able to suppress whatever that next instruction is and not have it bump up into the fetch register with the next clock tick. Let's take a look at how I might do that here. Okay, so my program ROM is a 256 kilobit or 32K byte EEPROM. This is parallel. This is different than the serial EEPROMs I'm using up here. It just so happens that this has the same pinouts as SRAM. Now what have I got going on here? Well, I've got my reset hold signal actually hooked up to my output enable so that when reset hold is high through an inverter on this board, basically disabling the output on the EEPROM. I also have here a chip enable signal that I can use. And my thinking is I should take the reset hold, tie that to chip enable, and then I should be able to use my output enable to be driven by the fetch suppress coming off of this control block here. Let's start by doing this in the emulator. So basically there's two changes here that need to be made. Change number one is I want to take the reset hold and tie that to the chip enable. So now with that change made, this should compile. Good. Now the second part of this is I need to create a function, a slot, in order to handle the fetch suppress. Now that should work. The last thing that I want to make sure that I take care of is in the assembler, and this is going to be in the tables where I change the jump to an immediate back down to be 2 bytes, 2 words, excuse me. So here is my test. So here's the least significant byte of the jump, the target, and then now my data word, which will indicate whether or not I've got a problem. Missed a step. So ultimately what I need to do is I need to connect my control logic midplane, signal fetch suppress, to my program ROM fetch suppress. Let's try that again. Okay, so that did break properly. There's my next break, which is fine. My jump. So there's my jump to my target, and my memory is actually pulling up the FF, but yes, it did actually load it. So the question then becomes, is fetch suppress actually tied in the control ROM? And for jump, no. So yes, it does actually suppress that there. Let me reprogram my program ROM, my control ROM 6, because that's where this particular control signal lives, and then we'll make these changes on real hardware. Okay, so my changes are going to be here around the program ROM, and I have my output enable pin here, 2 pins over is chip enable. Chip enable is pulled low. I want to disconnect that. And now I want to go ahead and tie those together because I want them driven from the same signal. And then I want that signal to be my current reset. My fetch suppress is here on pin 2, and I want to bring that down here to that location now. It's a little bit of a tight squeeze. But if that is what I believe it to be, that should work. Okay, let's give this a shot. So I'm still starting up in single step mode, and I'm going to have to figure out exactly how to handle that. But right now I'll take advantage of that. I'll step my way out of reset. There we go. Address 0 should be presenting a break instruction, which is there. And then that's my break instruction, and NOP. Address 2 should be presenting a jump instruction. No, I'm sorry, a second break. I have that incorrect. And then a couple of NOPs. There's my jump instruction in the fetch register. That progresses up to the instruction register. There's my jump target, and now I should be suppressing output off the program ROM so that when I step, I'm now fetching a NOP here, but my target address is 2. Nice. That's a good change. Well, this is very exciting. I'm actually executing code again on real hardware. It's taken me a bit to get back to this point, but I'm so thrilled to be here. Now, at this point, the size of the build is growing a little bit beyond what I can sustain. And so I'm going to start what I hope is only going to be a 4-part series to take the reset module, the clock module, the fetch register, and the instruction register, convert those into PCB, and then mount those onto the backplane. Now, I plan on doing each module in turn, likely combining the fetch and the instruction registers, and then a backplane independent of that. A 4-part mini-series within the series, if you will. With any luck, this will end up reducing the size of this footprint, and then I can move on to the registers. Now, I'm going to be working on all 4 of these in parallel so that I can do one order. So it is going to take me a little bit of time to get to the point where I'm ready to release my next video. In the meantime, I'll throw a link to the entire series. Have fun binging and catch up. Thank you again. See you soon.